And now in this lecture we'll answer two questions. In the first question we find out the area of this green shape, and in the second question we find out the length of line segment AP that is equal to x using two different methods. So we start with the first question. In the drawing we have a semicircle. BC equals to 10 units in its length, that is to say the diameter of the semicircle BC is equal to 10 units. Therefore the radius must be equal to half of it, that is to say the radius must be equal to 10 over 2, that is 5. In addition, we know that line segment BC equals to 8 units in its length. This is angle ABC, that is the right angle. Angle ABC equals to 90 degrees in its size. Again, our task is to find out the area of this green shape. So first of all, we join points P and B together by a straight line. By joining points P and P, we get peripheral angle BPC. Peripheral angle BPC subtends on BC, that is the diameter of the semicircle, and according to rule 5, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Let's it again on rule 5. According to rule 5, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. So in the drawing we have a circle. AB is the diameter of this circle. This is peripheral angle AEB that subtends on AB, that is the diameter of this circle, and therefore the size of this peripheral angle AB is equal to 90 degrees. So we can implement rule 5 in our drawing. Why? Because in our drawing we have peripheral angle BPC that subtends on BC, that is the diameter of this semicircle, and therefore according to rule 5, the size of peripheral angle BPC must be equal to 90 degrees. So in the next step we will implement the Pythagoras theorem on the right triangle BPC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. The hypotenuse on the right triangle BPC is BC, therefore the square of the hypotenuse is BC square, and BC square must be equal to PB square plus PC square. Okay, again, according to the Pythagoras theorem, in the right triangle PBC, BC square, that is the square of the hypotenuse, equals to PB square plus PC square. BC is 10, therefore BC square is 10 squared, it is 100. And it is equal to PB square. PB is the missing side, so we leave it as it is. So it is PB square plus PC square. PC is 8, therefore PC square is 8 squared, that is 64. So in total, if you found out that 100 equals to PB square plus 64. Here we subtract 64 from this equation. And you get that 100 minus 64 is 36, equals to PB square. PB square equals to 36. Here we take a root out of this equation and finally get that PB, the missing side PB, is equals to the square root of 36, that is 6. So the length of the missing side PB is equal to 6 units. This is inside PB. This is equals to 6 units in its length. It is given as the question that AC is a straight line. So if you focus on the left side of the straight line AC at point P, here the sum of the angles must be equal to 180 degrees according to all three. All three states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AC at point P? We have this angle, that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the right triangle APB, we define angle BAP. This angle is alpha. So this angle equals to alpha. This angle equals to 90 degrees. And therefore, this first missing angle must be equal to 90 degrees minus alpha. And again, this first missing angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. It is the sum of the angles in any triangle. What is the size of the missing angle PBC? Here, the big angle ABC is equal to 90 degrees in its size according to what is given in the question. We just right now found out that angle ABP equals to 90 degrees minus alpha. Therefore, this missing angle must be equal to 90 degrees minus 90 degrees minus alpha, that is alpha. Or in other way, you can say that alpha plus 90 degrees minus alpha equals to 90 degrees, that is the size of the big angle ABC. So this missing angle must be equal to alpha. So in the right triangle BPC, this angle equals to alpha, this angle equals to 90 degrees, therefore this missing angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. It is the sum of the angles in any triangle. So in the next step, we prove that the right triangle APB similar to the right triangle BPC according to angle similar to all. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So I shall prove that all the figures of the right triangle APB correspond equal to all the figures of the right triangle BPC, and therefore those two right triangles are similar to each other according to angle similar to all. So I write it down. I shall find out that the right triangle APB is similar. This is the sign of similar to the right triangle PBC according to angle similar to all. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle APB over side BC of the right triangle BPC is equal to side AP of the right triangle APB over side PB of the triangle PBC. And it is also equals to side PB of the triangle APB over side PC of the triangle PBC. Repeat again, from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side AB of the right triangle APB over side BC of the right triangle PBC is equals to side AP of the right triangle APB over side PB of the right triangle PBC. It is also equals to side PB of the right triangle APB over side PC of the right triangle PBC. AB is the missing side, so we leave it as it is. Over BC, BC equals to 10 units. And it is equal to AP. AP is the missing side, so we leave it as it is. Over PB. By the way, PB is the current side that belongs to both triangles. So over PB, PB is 6, and it is equals to PB again, that is 6, over PC. PC equals to 8 units in its length, according to what is given as the question. So in total, we should find out that AB over 10 equals to AP over 6 equals to 6/8. So those two expressions are equal to each other. Therefore, we create the first equation from those two expressions. So according to the first equation, we will get that AB over 10 equals to 6/8. Here we will multiply this equation 1 by 10. And we get that AB equals to 10 times 6 is 60 over 8. So we should find out that AB equals to 68, so 60 over 8. Here we will divide both the numerator and the denominator of this number by 4, and we get that 60 over 4 is 15, and 8 over 4 is 2. So in total we should find out that AB, the length of the missing side AB, is equal to 15 halves. So actually, this is the missing side AB that is equals to 15 half units in its length. We continue to focus on the long equation. Here, those two expressions are also equal to each other. Therefore, we get the second equation from those two expressions. According to the second equation, AP over 6 equals to 6/8. AP over 6 equals to 6/8. So here we will multiply this equation by 6, and we get that AP, according to equation 2, AP equals to 6 times 6 is 36 eighths. Here we divide both the numerator and the denominator of this number by 4, and we get that 36 over 4 is 9, and 8 over 4 is 2. So in total we should find out that AP equals to 9 half units in its length. According to equation 2, AP equals to 9 half units in its length. So this is inside AP, this is equals to 9 halves. In the next step, we define the center of this semicircle. This point is point O. The diameter of this semicircle is BC, that is equals to 10, therefore the radius is 5. The radius OB is 5. The radius OC is also 5. The next step, we join points O and P together by a straight line. OP is of course the radius of this semicircle, that is equals to 5. In the next step, we define angle BOP. This angle is theta. So in the next step, I will present to you the law of cosines, and we will implement the law of cosines in this triangle POB. The law of cosines is true in any triangle. So actually this is triangle ABC, that could be any triangle. Side AB of triangle ABC equals to A units, side AC equals to B units in its length, side BC equals to C units in its length, angle BAC equals to theta degrees in its size. According to the law of cosines, the following equation is true. In this triangle ABC, that could be any triangle. Cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So you can actually implement the law of cosines in triangle BOP. This is triangle BOP. This is angle theta. So according to the law of cosines, in this triangle BOP, the following equation will be true. That cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. So cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. Cosine theta equals to 5 squared. 5 squared is 25 plus 5 squared, that is 25. 25 plus 25 is 50. Minus 6 squared. 6 squared is 36. Therefore it is minus 36 over 2 times 5 times 5. 2 times 5 times 5 is 50. 50 minus 36 is 14 over 50. So in total we should find out that cosine theta equals to 14 over 50. We would like to find out the value of theta itself. So how can we find out the value of theta itself? Actually, we have the rule that the inverse function of a function cancels out the action of the function. Again, the inverse function of a function cancels out the action of the function. I'll give you an example. We know that the square, the function square, is the inverse function of the root. You can say also that the root is the inverse function of a square. So the root cancels out the action of the square. Again, the root cancels out the action of the square. So we give you an example. If we take number 3 and we square it, the result will be 9. Now, in order to get back number 3 again, we just have to operate the inverse function of a square that is a root on the result, and we get that the result is 9, so the square root of 9 is 3. That is to say, the root cancels out the action of a square. In this way, we get the original number 3 again. So, we have here angle theta. We operated the function cosine on angle theta, and the result is 14/50. In order to find out the value of theta, again, we just have to operate the inverse function of cosine on the result, that is 14/50. The inverse function of cosine is arc cosine. So we operate the inverse function arc cosine on the result, that is 14/50. In this way we get the size of angle theta again. Exactly like this example, we operated the inverse function of a square that is the root on the result, that is 9. In this way we get number 3 again. Number 3 is the number that we have before the operation of the square on it. Okay, and we got number 3 again by the action of operating the inverse function of a square that is the root on the result, that is 9, and the square root of 9 is 3. In this way, we operated the inverse function of a cosine, that is arc cosine, on the result, that is 14/50. In this way, we get angle theta back again. And the arc cosine of 14/50 you can find out by calculating it in any simple scientific calculator. You get that arc cosine of 14/50 is equal to theta is equal to 73.74 degrees in its size. So if you found out that the size of this angle theta is 73.74 degrees. Our task is to find out the area of this ring shape. In order to find out the area of this ring shape, we have to find out, first of all, the area of segment BP. This is segment BP. So what is the area of segment BP? From the drawing, it is very easy to see that the area of segment BP is equal to the area of sector BOP. Minus the area of triangle BOP. Okay, again, I should find out that the area of segment BP equals to the area of sector BOP minus the area of triangle BOP. What is a sector? A sector is a portion of a circle with two radii and the arc between them. And again, the green shape AOB is a sector. Sector AOB consists of two radii and the arc AB between the two radii. It also consists of angle theta, that is the angle between the legs of the sector. And the area of this sector, sector AOB, here the rounded line above AOB is the sign for a sector. The area of sector AOB is equal to pi r squared, that is the area of the circle that contains the sector, times theta, that is the angle between the legs of the sector, over 360 degrees. Okay, again, the area of the sector AOB equals to pi r squared times theta over 360 degrees. We use the new formula in order to find out the area of this sector, sector BOP. We already found out that angle theta equals to 73.74 degrees in its size. Actually, this is angle theta, that is the angle between the legs of sector BOP. It equals to 73.74 degrees in its size. The legs of the two radii, OP equals to OB, the legs of the circle of the two radii, that each of them is equal to 5. BO equals to 5, OP also equals to 5. So according to the new formula that I presented to you, the area of this sector BOP must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the circle, that is 73.74 degrees, over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25, therefore pi r squared is 25 pi, times 73.74 degrees over 360 degrees. So the value of this expression in total it is equal to 16.088 square units. So if you found out that the area of this sector BOP is equal to 16.088 square units. Minus the area of this triangle BOP. BO equals to 5, PO equals to 5, BP equals to 6, according to what we already found out. Triangle BOP is an associated triangle because of the fact that side BO equals to side PO equals to 5. The base of this associated triangle BOP is BP. So, in order to find out the area of this associated triangle BOP, from the vertex O, we draw perpendicular on the base PB. So here, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point O and the base PB. This point is point M. We have the rule that the perpendicular to the base of an associated triangle bisect the base. The base is PB. PB is the base of the associated triangle POB. So, according to the rule that I mentioned, the perpendicular OM bisects base PB. PB in total is 6, therefore each half must be equal to 3. The first half PM is 3, and the second half MB is also 3. we have to find out the height OM. In order to find out the height OM, we just have to implement the Pythagoras theorem on the right triangle PMO. According to the Pythagoras theorem and the right triangle PMO, 5 squared, that is the square of the hypotenuse, equals to PM squared, that is 3 squared, that is 9, plus OM squared. 5 squared is 25, equals to 9 plus OM squared. Here we subtract 9 from this equation and we get that 25 minus 9 is 16 equals to OM squared. OM squared equals to 16. Here we take a root out of this equation and finally we get that OM equals to 4 units in itself. The height OM is equals to 4. Therefore, now it is very easy to find out the area of this isosceles triangle BOP. According to the rule, the area of any triangle equals to the base of the triangle times the height to the base over 2. Therefore, the area of this isosceles triangle BOP is equals to the base BP times the height to the base OM. OM is the height to the base because it creates 90 degrees with the base PB over 2. BP is 6, the base BP is 6, times the height OM is 4, divided by 2. 4 over 2 is 2, and 2 times 6 is 12. So in total we found out that the area of this isosceles triangle POB is equal to 12 square units in its size. So the area of segment BP equals to the area of sector POB, that is 16.088, minus the area of the isosceles triangle BOP, that is 12. 16.088 minus 12 is equal to 4.088. So if you found out that the area of this segment BP is equal to 4.088 square units in its size. The area of this segment BP is equal to 4.088 square units in its size. Our task is to find out the area of this green sheet. This is segment BP. And the area of this segment BP is equal to 4.088 square units in its size. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of the right triangle APB minus the area of segment BP. Again, the area of the green shape equals to the area of the right triangle APB minus the area of this segment BP. So write it down. If you found out that the area of segment, the area of the green shape equals to the area of the right triangle ABP. Minus the area of segment BP. Because again, we found out that the area of the green shape equals to the area of the right triangle APB minus the area of segment BP. AP equals to 9 over 2 is 4.5. Side BP equals to 6 units in its length. So the area of this right triangle APB equals to the base of the triangle, that is AP, times the I to the base, that is PB over 2. AP is 4.5, PB 6 divided by 2. 4.5 times 6 is 27, and 27 over 2 is 13.5 square meters. So if we found out that the area of this right triangle APB is equals to 13.5 square meters. And we already found out that the area of this segment BP is equals to 4.088 square meters in its size. So 13.5 minus 4.088 is equal to the area of the green shape, that is actually 9.142 square meters. We check again. 13.5 minus 4.088 is equal to 9.412 square meters. So if you found out the area of the green shape, is equal to 9.412 square meters. And again, if you found out that the area of the green shape equals to 9.412 square meters in size. So we finish with the first question. In the next step, I present to you the second question, and we solve the second question using two different methods. In the second question, our task is to find out the length of line segment AP is equals to x. We have to find out the value of x. So in the drawing we have a semicircle, AB equals to 10, that is to say the diameter of this semicircle equals to 10 units in its length. Line segment BC equals to 6 units in its length. In addition, we know that AP equals to PC equals to x. Again, our test is to find out the length of AP that equals to x. We have to find out the value of x. So in the first step, we define the center of this semicircle. This point is point O. The diameter of this semicircle is 10, therefore the radius must be equal to 5. The radius OO is 5. The radius OB is also 5. In the next step, we will join points O and P together by a straight line. OP is, of course, the radius of this semicircle that is equals to 5 units in its length. By doing all those constructions, we can deduce the associated triangle, triangle AOP. Why triangle AOP is an associated triangle? Because side AO equals to side OP equals to 5. And we have the rule that says that in front of equal sides in a triangle, there are equal angles. If we relate to the associated triangle, triangle AOP, we get that in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the associated triangle, triangle AOP, alpha plus alpha is 2 alpha, therefore this third missing angle must be equal to 180 degrees minus 2 alpha. According to the rule, it says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, the big right triangle APC is an associated triangle because side AP equals to side PC equals to X. So therefore, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. But we have only found out that the size of this angle is alpha. Therefore, the size of this angle must be also equal to alpha because they are equal to each other. So in the right big triangle, the big associated triangle APC, alpha plus alpha is 2 alpha. Therefore, the size of this vertices angle must be equal to 180 degrees minus 2 alpha. According to the third rule, it said that the sum of the angles in any triangle is equal to 180 degrees. So the size of the first missing angle must be equal to 180 degrees minus 2 alpha. In the next step, I'll copy the big associated triangle APC and the small associated triangle AOP and MUP, and we prove that those two associated triangles are similar to each other according to angle similarity rule. What is the length of side AC of the associated triangle APC? From the law, it is very easy to see that AC in total equals to 10 plus 6, that is 16. So AC equals to 16 is in its length. Roughly, those are the two associated triangles that are coming from the original drawing. This is the big associated triangle APC, and this is the small associated triangle AOP. So why those two associated triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So if you prove that all the angles of the big triangle, the big associated triangle APC are correspondingly equal to all the angles of the small associated triangle AOP. And therefore those two associated triangles are similar to each other according to angle similarity rule. So I write it down. We should found out that the big associated triangle APC is similar. This is the sign of similar to the small associated triangle AOP, according to angle similarity rule. And from the fact that those two associated triangles are similar to each other, We derive that the following relationship exists between their sides. Hello?
בוקר טוב, שלום, מה נשמע?
Who is speaking?
אני מזכירה לך תור מחר ב-2:10.
Okay, I'm in the middle of the Zoom lesson, so okay, I will come tomorrow, okay? Thank you very much.
Okay, thank you.
Okay.
Bye.
So from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AC of the big associated triangle APC over side AP of the small associated triangle AOP is equal to side PC of the associated triangle APC over side PO of the small associated triangle AOP. Okay, repeat again. From the fact that those two associated triangles are similar to each other, we derive the following relationship exists between their sides. That side AC of the big associated triangle APC over side AP of the small associated triangle AOP is equal to side PC of the big associated triangle APC over side PO of the small associated triangle AOP. AC is 16 over AP is X, and it is equals to PC is also X, over PO equals to 5. So in total, if you found out that 16 over X equals to X over 5. Here we cross multiply this equation, and we get that X times X is X squared equals to 16 times 5. So X squared equals to 16 times 5. Here we take a root out of this equation, and finally we get that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we're left only with 5. So it is 4 times square root of 5. 4 times square root of 5 is 8.94 units. So in total, we found out that the length of this line segment AP is equal to X. It is equal to either 4 times square root of 5 units in its length. From terms of numbers, the length of this line segment AP is equal to X is equal to 8.94 units in its length. So we finish with the first method. In the next step, I present to you how to find out the length of line segment AP is equal to X using a second method. So in the second method, we use the rule that we already used in the first question. The rule said that the perpendicular to the base of an isosceles triangle bisects the base. Triangle APC is an isosceles triangle because side AP equals to side PC equals to x. So, according to the rule that I mentioned, so from the vertex P, we draw perpendicular on AC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point P and AC. This point is point M. According to the rule that I mentioned, the perpendicular PM bisects the base AC. AC in total equals to 10 plus 6, that is 16. So the base AC of the isosceles triangle APC equals to 16 units in its length. So the perpendicular PM bisects the base AC. AC is 16, therefore each half must be equal to 8 units in its length. The first half AM is 8 and the second half MC is also 8. According to the rule that I mentioned. AM equals to 8 units in its length, MC also equals to 8 units in its length, according to the rule that I mentioned. In the next step, we define the center of this semicircle. This point is point O. And we join points P and O together by straight line. PO is of course the radius of the semicircle. This is equals to 5 units. OA is also the radius of the semicircle, that is equal to 5. OB is also the radius of the semicircle, that is equal to 5. So what is the length of this line, small line segment OM? From the law it is very easy to say that OM equals to AM minus AO. So OM equals to AM minus AO. OM equals to AM. AM equals to 8 units in its length minus AO. AO is 5. So OM equals to 8 minus 5, that is 3. OM equals to 3 units in its length. OM equals to 3 units. In the next step, I'll copy the right small triangle AOM in a new page and we'll implement on it the Pythagoras theorem. The hypotenuse PO equals to 5 units in its length. OM equals to 3 units in its length. And the missing side is side PM. So here by PT is the abbreviation for Pythagoras theorem. So this is the small right triangle OPM that according to the original drawing. According to the Pythagoras theorem, in this right triangle OPM, or P squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. So I write it down. Or P squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. OP equals to 5, therefore OP squared is 5 squared, that is 25. And it is equals to PM squared. PM is the missing side, so we will this it is. Plus OM squared. OM equals to 3, therefore OM squared is 3 squared, that is 9. So today we should find out that 25 equals to PM squared plus 9. Here we subtract 9 from this equation, and we get that PM squared equals to 25 minus 9, that is 16. So PM squared equals to 16. Here we take out of this equation, and finally we get that PM equals to the square root of 16, that is 4. So PM equals to 4 units in its length. This is the missing side PM, that equals to 4 units in its length. So in the next step, I'll copy the big right triangle APM in a new page, and we will implement on it the Pythagoras theorem. AM equals to 8 units in its length. The hypotenuse AP equals to X units in its length, that is the line segment that we are looking for this question. And PM equals to 4 units in its length. So actually, this is the right big triangle APM that is copied from the original drawing. According to the Pythagoras theorem, in this right triangle APM, AP squared, that is the square of the hypotenuse, equals to PM squared plus AM squared. AP squared equals to PM squared plus AM squared. AP equals to X, therefore AP squared is X squared and is equals to PM squared. PM equals to 4, therefore PM squared is 4 squared, it is 16, plus AM squared. AM equals to 8, therefore AM squared is 8 squared, it is 64. So in total, we found out that x squared equals to 16 plus 64, that is 80. X squared equals to 80. Here we take a root out of this equation, and finally we get that x equals to the square root of 80. We substitute 80 by 16 times 5. So x equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So in total we should find out that x in both methods, that x equals, that AP is equals to x, it is equals to either 4 times square root of 5, or in terms of numbers it is equals to 8.94 units in its length. Repeat again, in both methods we found out that the length of this line segment AP is equals to x, it is equals to either 4 times square root of 5 units in its length, or in terms of numbers it is equals to 8.94 units in its length. So we finish with the second question. In the next step I will summarize the lecture. Let's start with the first question, of course. In the first question, our task is to find out the area of this green shape. So in the drawing, we have a semicircle. BC equals to 10, that is to say the diameter of this semicircle equals to 10 units in length. We also know that PC equals to 8 units. This is an angle ABC, that is a right angle. Again, our task is to find out the area of this green shape. So in the first step, we join points P and B together by straight line. By joining points P and B, we created peripheral BPC. Peripheral BPC subtends on BC, that is the diameter of the semicircle, and according to Rule 5, any peripheral that subsets on the diameter of the semicircle or circle must be equal to 90 degrees in its size. Therefore, according to Rule 5, peripheral BPC is a right angle. So in the next step, implemented the Pythagoras theorem on the right triangle BPC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the hypotenuse of the right triangle BPC is BC, therefore the square of the hypotenuse is BC square, and BC square equals to BP square plus PC square. Repeat again. According to the Pythagoras theorem, in the right triangle BPC, BC square, that is the square of the hypotenuse, equals to PB square plus PC square. BC is 10, therefore BC square is 10 squared, it is 100, and it is equals to PB square. PB is the missing side, so we leave it as it is, plus PC square. PC is 8, therefore PC square is 8 squared, that is 64. So in total we should find out that 100 equals to PB square plus 64. Here we subtracted 64 from this equation, and finally found out that 100 minus 64 is 36. So PB square equals to 36. Here we took out of this equation and finally found out that PB equals to the square root of 36, that is 6. So this is the missing side PB, this equals to 6 units in its length. It is given us the equation that AC is a straight line. So if you focus on the left side of the straight line AC at point P, here the sum of the angles must be equal to 180 degrees according to Rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AC at point P? We have this angle, that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the right triangle APB, we define angle BAP. This angle is alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. It is given as a question that the big angle ABC is the right angle. This is the right angle. And you just write down further that angle ABP equals to 90 degrees minus alpha. Therefore, this missing angle must be equal to 90 degrees minus 90 degrees minus alpha. This is alpha. Or you can see it another way, why this angle must be equal to alpha, because alpha plus 90 degrees minus alpha is 90 degrees. This is the size of the big angle ABC. Therefore, this missing angle must be equal to alpha. So in the right triangle BPC, this angle equals to alpha, this angle equals to 90, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. So in the next step, we prove that the right triangle APB is similar to the right triangle BPC according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if we found out that all the triangles of the right triangle APB are correspondingly equal to all the triangles of the right triangle BPC, and therefore those two right triangles are similar to each other according to angle similarity rule. Okay, again, if we found out that the right triangle ABP is similar to the right triangle PBC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle ABP over side BC of the right triangle BPC is equal to side AP of the right triangle APB over side PB of the right triangle PBC, and it is also equal to side PB of the right triangle APB over side PC of the right triangle PBC. Okay. We know that AB over BC equals to AP over PB equals to PB over PC. In the numerator of each expression, we have the size of the right triangle BP, and in the numerator of this expression, we have the size of this right triangle BPC. So AB over BC equals to AP over PB equals to PB over PC. AB is the missing side, so we leave this it is. Over BC, BC equals to 10, and AP is the missing side, so we leave this it is. Over PB, PB equals to 6, and we have PB again, that is 6, over PC, PC is 8. So in total, we should find out that AB over 10 equals to AP over 6 equals to 6 eighths. Those two expressions are equal to each other. Therefore, look at the first equation from those two expressions. According to the first equation, AB over 10 equals to 6 eighths. Here we multiply this equation 1 by 10, and finally found out that AB equals to 10 times 6, that is 60 over 8. So AB equals to 60 over 8. Here we divided both the numerator and the denominator of this number by 4. 60 over 4 is 15, and 8 over 4 is 2. So in total, AB equals to 15 halves. So side AB equals to 15 halves units in its name. Those two expressions are also equal to each other. So we gathered the second equation from those two expressions. According to the second equation, AP over 6, actually those two expressions are equal to each other. So we gathered equation 2 from those two expressions. According to equation 2, AP over 6 equals to 6 eighths. AP over 6 equals to 6 eighths. Here we multiply this equation 2 by 6. We finally found out that AP equals to 6 times 6, that is 36 over 8. Here we divided both the numerator and the denominator of this number by 4, and finally found out that 36 over 4 is 9, and 8 over 4 is 2. So in total we found out that AP equals to 9 halves. So this is the is inside AP, this is equals to 9 halves units in its length. We define the center of this semicircle, this point is O. The diameter is 10, therefore the radius OB is 5, the radius OC is also 5. The joint points OP together by straight line OP is also the radius of this semicircle, that is equals to 5 units in its length. We defined angle POB, this angle is theta. Then I presented to you the law of cosines, and we implemented the law of cosines in this triangle, triangle POB. Actually, the law of cosines is true in any triangle. This is triangle ABC that could be any triangle. The length of side AB is A units, side AC equals to B units in itself, and side BC equals to C units in itself. This is angle BAC that is equals to theta degrees in its size. So in this triangle, triangle ABC that could be any triangle, the following equation is true. That cosine theta equals to A square plus B square minus C square over 2 times A times B. Again, cosine theta equals to A square plus B square minus C square over 2 times A times B. Okay? The next step we implemented the law of cosines. This triangle, triangle POB. According to the law of cosines, in triangle POB, the following equation is true. That cosine theta equals to 5 square plus 5 square minus 6 square over 2 times 5 times 5. And again, in the right triangle POB, the following equation is true. That cosine theta equals to 5 square plus 5 square minus 6 square over 2 times 5 times 5. So 5 square is 25, plus 5 square that is 25. 25 plus 25 is 50, minus 6 square. 6 square is 36, so in total the numerator we have 50 minus 36, that is 14. In the denominator we have 2 times 5 times 5, that is 50. So in total we actually found out that cosine theta equals to 14 over 50. Cosine theta equals to 14 over 50. We would like to find out the value of theta itself. So in order to find out the value of theta itself, we implemented here the rule that states that the inverse function cancels out the action of the function. Again, the inverse function cancels out the action of the function. Here we know that the root is the inverse function of a square. So if we take number 3 and we square it, the result is 9. Now in order to get back number 3 again, we just have to operate on the result, the inverse function of a square that is a root, and the square root of 9 is 3. So by operating the inverse function of a square on the root, we get back number 3 again. Why? Because the root cancels the action of a square, and this way we get back number 3 again. So the inverse function cancels out the action of the function. According to the new rule, cosine theta equals to 14 over 50. We would like to get angle theta back, yes? So, therefore, we have to operate the inverse function of cosine, that is our cosine on the result, that is 14 over 50. In this way, we get angle theta back again. So, our cosine of 14 over 50 equals to the size of angle theta. And our cosine of 14 over 50 equals to theta. Therefore, theta equals to 73.74 degrees in its size. So this is angle theta, that is equals to 73.74 degrees in its size. Our task is to find out the area of this green shape. In order to find out the area of this green shape, we have to find out, first of all, the area of segment VP. So what is the area of segment BP? Actually, the area of segment BP equals to the area of sector BOP minus the area of triangle BOP. Again, this segment BP equals to the area of sector BOP minus the area of this triangle POB. This again, the area of segment BP. This is segment BP. The area of segment BP equals to the area of sector BOP minus the area of triangle BOP. So what is a sector? A sector is a portion of a circle with two radii and the sector between them, and the arc between them. Again, a sector is a portion of a circle with two radii and the arc between them. The green shape AOB is a sector. Sector AOB consists of two radii and the arc AB between the two radii. The two radii also define the legs of the sector. Angle theta is the angle between the legs of the sector, and the area of this sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. So we use the new formula in order to find out the area of this sector BOP. According to the new formula, the area of this sector BOP equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 73.74 degrees, over 360 degrees. R is 5 because PO equals to OB equals to R, that is 5. Therefore, R squared is 5 squared, that is 25. Pi r squared is 25 pi times 73.74 degrees over 360 degrees. So the value of this expression in total it is equals to 16.088. So we should find out that the area of this sector BOP is equals to 16.088 square units in size. So what is the area of this triangle POB? Actually, triangle POB, first of all, is an associated triangle because side PO equals to side OB equals to 5. The base of this associated triangle POB is PB. In order to find out the area of this triangle, the associated triangle POB, from the vertex O, we go perpendicular on the base PB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and PB. This point is point M. And remember the rule that the perpendicular to the base of an associated triangle bisect the base. So the perpendicular OM bisect the base PB. PB is 6, therefore each half must be equal to 3. The first half is PM, that is 3, and the second half is MB, that is 3. So in the next step, we implemented the Pythagorean theorem on the right hand OMB. According to the Pythagorean theorem, PO squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. PO is 5, therefore PO squared is 5 squared, that is 25. And it is equals to PM squared. PM is 3, therefore PM squared is 3 squared, that is 9, plus OM squared. OM is the missing side, so we leave it as it is. Here we subtract 9 from this equation, and find out that OM squared equals to 25 minus 9 is 16, so OM squared equals to 16. Here we took out of this equation and found out that OM equals to the square root of 16, that is 4. So OM equals to 4. Now it is very easy to find out the area of this associated triangle, triangle POB. The area of any triangle equals to the base of the triangle times the height over 2. The base is PB, that is 6, the height is OM, that is 4. The area of associated triangle POB equals to the base PB times the height OM over 2. PB is 6, OM is 4 over 2. 4 over 2 is 2, and 2 times 6 is 12. So total, actually found out that the area of this associated triangle POB is equals to 12 square units. Now the area of segment BP equals to the area of sector POB, that is 16.088, minus the area of the associated triangle POB, that is 12. 16.088 minus 12 is 4.088. So in total we should find out that the area of this segment BP is equals to 4.088 square units in its size. Our task is to find out the area of this green shape. The area of this green shape equals to the area of the triangle PB minus the area of this segment PB. Okay, again, the area of the green shape equals to the area of the right triangle APB minus the area of segment BP. The area of this right triangle APB equals to the base of the triangle that is AP times the height that is PB over 2. AP is 4.5, PB is 6 divided by 2. 4.5 times 6 is 27, and 27 over 2 is 13.5. So in total we shall find out that the area of this right triangle APB is equal to 13.5 square units in its size minus the area of segment BP. The area of segment BP equals to, we already found out that the area of segment BP equals to 4.088 square units in its size. So 13.5 minus 4.088 is 9.412. So we found out that the area of this green jet is equal to 9.412 square units in its size. So we finished with the first question. In the next step I presented to you the second question, and we solved the second question in two different methods. In the second question, our task is to find out the length of line segment AP that is equal to x. We have to find out the value of x. So in the drawing we have a semicircle. We know that AB equals to 10, that is to say the diameter of the semicircle is 10 units. Line segment BC equals to 6, and AP equals to PC equals to x. Again, our task is to find out the length of AP that is equal to x. So first of all, we define the center of the semicircle. This point is O. The diameter AB is 10, therefore the radius is 5. The radius OA is 5, the radius OB is 5. We join points O and P together by straight line. OP is also the radius of this semicircle, that is 5. By doing all those constructions, we created the associated triangle, triangle POA. Why triangle POA is the associated triangle? Because OP equals to OA equals to 5. And we have the rule that it states that in front of equal sides in the triangle there are equal angles. So if we relate to the associated triangle, triangle AOP, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the associated triangle, triangle AOP, alpha plus alpha is 2 alpha, and therefore this perpendicular angle must be equal to 180 degrees minus 2 alpha, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big associated triangle, triangle APC, why triangle APC is an associated triangle? Because AP equals to PC equals to x. So in the big associated triangle, triangle APC, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. But we have only found out that the size of this angle is alpha, therefore the size of this angle must be also equal to alpha because they are equal to each other. So in the big associated triangle, triangle APC, alpha plus alpha is 2 alpha, therefore this perpendicular angle must be equal to 180 degrees minus 2 alpha, according to the sum rule that said that the sum of the angles in any triangle is equal to 180 degrees. So in the next step I call it the big associated triangle, triangle APC, and the small associated triangle, triangle AOP and AOP, and we prove that those two associated triangles are similar to each other according to angle similarity. So those are the two associated triangles that are coming from the original drawing. Why those two associated triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So if we prove that all the fingers of the big associated triangle, triangle APC are correspondingly equal to all the fingers of the small associated triangle, triangle AOP. And therefore those two associated triangles are similar to each other according to angle similarity rule. And for the fact that those two associated triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AC of the associated triangle, triangle APC over side AP of the associated triangle, triangle AOP is equal to side PC of the big associated triangle, triangle APC over side PO of the small associated triangle, triangle AOP. AC 16, AP is X, PC equals to X also over PO. PO is 5. So in total, I should have found out that 16 over X equals to X over 5. Here, of course, multiply this equation and finally found out that X times X is X squared equals to 16 times 5. Here we took out of this equation and finally found out that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So in total we should found out that that AP is equals to X, it is equals to either 4 times square root of 5, and 4 times square root of 5 is also 8.94 units. Okay, again, I should find out that AP it is equal to x, it is equal to either 4 times square root of 5 units, or in terms of numbers, AP is equal to x equals to 8.94 units in itself. We finish with the first method. In the next step, presented to the second method. In the second method, we use the rule that the perpendicular to the base of an isosceles triangle bisect the base. Again, the perpendicular to the base of an isosceles triangle bisect the base. Triangle APC is an isosceles triangle because AP equals to PC equals to x. So from the vertex P, we draw perpendicular to AC. AC in total equals to 10 plus 6, that is 16. So the base AC equals to 16. From the vertex P, we draw perpendicular to the base AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P in the base AC. This point is point A, M. So according to the rule that I mentioned, the perpendicular PM bisects AC. AC is 16, therefore each half must be equal to 8. The first half AM is 8, and the second half MC is also 8. So we define the center of this semicircle. This point is point O. The diameter AB is 10, therefore the radius is 5. The radius OM is 5, the radius OA is 5, the radius OP is also 5. So the length of this small line segment OM is equal to AM minus AO. Again, OM equals to AM minus AO. AM is 8, AO is 5, so OM equals to 8 minus 5, that is 3. OM equals to 3 units in its length. In the next step, I copy the right triangle OPM in the new page and implemented on it the Pythagoras theorem. This is the right triangle OPM that I copied from the original drawing. According to the Pythagoras theorem, PO square equals to PM square plus OM square. PO is 5, therefore PO square is 5 square, that is 25, and it is equals to PM square. PM is the missing side, so leave it as it is, plus OM square. OM is 3, therefore OM square is 3 square, that is 9. So in total, we actually found out that 25 equals to PM square plus 9. Here we subtract 9 from this equation, and we found out that PM square equals to 25 minus 9 is 16. So PM square equals to 16. Here we took out of this equation, and we found out that PM equals to the square root of 16, that is 4. So this is the missing side PM, this equals to 4. In the next step, I copied the right triangle PMC in the new page and implemented on it the Pythagoras theorem. The right triangle APM in the new page and implemented on it the Pythagoras theorem. This is the right triangle APM that I copied from the original drawing. According to the Pythagoras theorem, AP square equals to PM square plus AM square. AP square equals to PM square plus AM square. AP is x, therefore AP square is x square, and it is equals to PM square. PM is 4, therefore PM square is 4 square, that is 16, plus AM square. AM is 8, therefore AM square is 8 square, that is 64. X square equals to 16 plus 64, that is 80. X square equals to 80. Here we took out all the expression and found out that x equals to the square root of 80. We substitute 80 by 16 times 5, so x equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we have to only be 5. So in both methods we actually found out that the length of line segment AP is equals to x. This is equal to either 4 times square root of 5 units in itself, or in terms of numbers, AP that is equal to x is equal to 8.94 units in its length. Okay, thank you very much.